This is APAB. We're doing the Intro to BC unit. That's ITBC. We're doing topic number 1, which is parts. So we're in example 3, which is actually identical to example 2, but with the fancy shortcut. So there's a cool shortcut to parts that if you have a u that is going to derive away to 0, which not every function does, right? So for instance, e to the x is going to keep deriving to e to the x. It'll never derive to 0. Sine and cosine, they just keep looping, right? All the other trig functions, they don't derive to 0, right? Because like derivative of tangent is secant squared, and then derivative of secant squared is going to be a real pain, and etc. Right? But what does derive to 0 are x to the n's, where n is a positive integer, right? So like square root of x does not derive to 0 because there's no time when that power of x is going to hit 0, and then once that power of x hits 0, you've got a constant, and once you derive the constant, it's gone. So really, the shortcut only works if you have an algebraic term as your u that is an x to a positive whole numbered power, right? So that's the short answer. But so we already know that this is my u from the last problem, right? And we know that this is my dv. So in this case, my u, x squared, will derive to 0 eventually, right? And not even like way down the road, right? Like if you derive x squared a couple times, boom, it's gone. So here's the cool trick that you can use if you have this opportunity. So you're going to have a derive column or a differentiate column, right? And it's going to be your u's, and you're going to have an integrate column, right? And it's going to be your dv's. So I'm going to start by listing my u, which is x squared, and my dv, which is a sine of x, right? I'm now going to derive my u column until it gets to 0. So the derivative of x squared is 2x, the derivative of 2x is 2, the derivative of 2 is 0. That's where I'm going to stop. I'm going to stop when it hits 0. I'm then going to do the same thing on the integration column. I'm going to integrate until I get to that same row where my derivative zeroed out, which is, again, why it's important that to do this trick, you have to hit 0. Otherwise, you'd just be deriving forever. So I'm going to integrate, right? I'm going to integrate, so when I anti-derive, right, I'm going to get negative cosine of x, negative sine of x, regular cosine of x. Cool. Okay. So now here's the part you have to memorize, right? You're going to go on the diagonal. So you're going to go from the x squared to 1 below it, all right? And it's going to get a plus sign. So the term I'm going to get from this is a positive times x squared negative cosine x. So that will net a negative x squared cosine of x, because even though it had a positive here, the whole thing nets negative, right? The next row, right, and this is the part we have to be careful about. So when we do the next little line, right, from top to bottom, we're going to alternate the signs, and it's going to be a negative. So this one is going to end up being a negative times a negative 2x sine x. So that's going to come out positive. So 2x sine of x, right? And then I'm going to go back to positive, right? So this is going to go back to being positive. So I'm going to end up with this being a plus 2 cosine of x, right? And then as you can see, if I tried to do the next one, it wouldn't matter because it's going to be 0. That's the whole point, right? I have a 0 times, it doesn't matter what I'm multiplying by, it's gone. So these end up being my 3 terms, and I just need to tack on my plus c. Now I want you to look how I kept the answer from the last problem. I kept the example 2 answer here so that you could compare. In blue, I have a negative x squared cosine of x. Oh, hey, that's the first term here. Plus a 2x sine x. Oh, hey, that's the next term. Plus a 2 cosine x. Hey, that's the next term. And then don't forget the plus c. So the shortcut's really helpful and totally awesome. Now, this is the kind of situation where they could ask you to do a lot more rounds of parts. So when I said in the last example that it's unlikely they will ask you to do more than 2 rounds of parts, there are things that do not work with this shortcut. If it doesn't work with this shortcut, I don't anticipate you having to do more than 2 rounds of parts. If it does work with this shortcut, they could give you as many rounds as they want. They could make this take 8 things to derive because all you're doing is deriving and integrating, and then you're fine. You just write the answer. So the shortcut makes it much faster and means that they could, in theory, give you more repeated efforts of parts to get to the answer because of the shortcut.